All right. The first things we're going to talk about related to addition are some properties. These are properties you've probably heard of before, but we want to make sure we refresh your memory, make sure you have a really solid understanding of these properties. The first of these is commutative. And what commutative property is about is order. That is the idea that 7 plus 3 is equal to 3 plus 7. What we've done here is we have changed the order of the terms that are in the addition problem. Right now, we're just talking about addition. So we're talking about these properties in terms of addition, and this is the commutative property. It's about order. We're changing the position of things. I have to take a little side note here, and you may have seen this in the weekly update. Please do not ever call this the commutative property. There is no N anywhere in the word. The root here, the idea is that we are moving things. The 7 and the 3 switch places. They have moved. They commuted. They moved from one place to another. So there is no N anywhere in this word. Please do not say commutative, because there is no commutative property. We're not talking about a community. We're talking about things that have moved. They have commuted. They have changed places. That's the commutative property. In more general terms, and we'll do this with the properties we talk about, we have 7 plus 3 equals 3 plus 7 as our example, but in more general terms, what we're saying is with regard to addition, A plus B is equal to B plus A. We can change the order and the value stays the same. As we go through these properties, if you see anything that you want to ask about, please don't hesitate. For the most part, they're almost like learning definitions as we go through the properties. The associative property. The associative property is about grouping. For example, if we say 2 plus 3 plus 5, that is equal to 2 plus 3 plus 5. And just to sort of prove that to you, we'll take a little detour here just for a second. On the left-hand side, we would do what's in parentheses first, following order of operations. So we would have 8. So this would be 2 plus 8, which would be 10 on the left-hand side. On the right-hand side, we would do what's in parentheses first. 2 plus 3 is 5 plus 5. Sure enough, that's also 10. So the way we have grouped the numbers doesn't change the fact that they are still equal. 2 plus 3 plus 5 is equal to 2 plus 3 plus 5. Really important note here about the associative property. The associative property is about grouping. It's not about parentheses. Parentheses are involved, but it's not about the fact that there are parentheses in there. It's which numbers have been grouped together. On the left-hand side, the 3 and the 5 have been grouped together. On the right-hand side, the 2 and the 3 have been grouped together. Since the grouping changed, that's how we know this is an example of the associative property. And then our general way of writing the associative property is going to be A plus B plus C is equal to A plus B plus C. We've changed the grouping, but the left and right hand sides of the equation remain equal. That's the associative property. Up next, we have the identity property. The identity property basically says, is there a number you could add to something without changing the value to have it keep its identity? And I'll ask you that. Is there a number that we could add to something and it would keep its identity? Its identity wouldn't change, its value would stay the same. Very good, Leslie, Natalie, Moylan, thank you. 0. So if I say 7 plus 0 equals 7, that's an example of the identity property. 7 plus 0 equals 7. The identity of the number hasn't changed. You might hear somebody say for addition, 0 is the identity element. That's not something that we'll really focus on in our course, but you might hear it somewhere down the line. For addition, 0 is the identity element because it's the thing you can add to a number and not change its value. One thing, it says must work both ways. What that means here is this. 7 plus 0 gives me 7. In order for the identity property to be in place, in order for us to say this is the identity property of addition, it has to work the other way too. And what I mean by that is 0 plus 7 equals 7. The 0 could be on the right-hand side, or the 0 could be on the left-hand side. It has to work both ways in order for it to be called the identity property. And this is the identity property of addition. And if we were going to write that in general form, we would just say, make a better A there, A plus 0 is equal to A. So what we have here is we have these three general properties: commutative, associative, and identity. And they all work with addition. Any questions about those before I ask you a question? Okay. I'm going to do a poll for this one. What property is shown in the equation that you've been given? While I'm typing this in, I'm going to remind you to be very careful when you make your choice. Okay. What property is shown in that example? This is a case where I said I'd go a little quicker today than we normally do. Let's go another 10 seconds on this poll and then we'll talk about it. See what we've got. Okay, we're kind of split between commutative and associative. To be honest, that's kind of what I expected. In some ways, for right now, you might call this a trick question. After we do this, you can no longer call it a trick question. And here's what's going on here. Remember I said that associative, oops, let me do a better job with that, is not about parentheses. If you see parentheses in there, it could be an associative property, but it might not be. And if we take a look at this, what has changed? If the grouping changed, then it's associative. If the order changed, then it's commutative. And as I look at this, 1 and 4 are grouped together. 1 and 4 are still grouped together. The grouping did not change. What changed was the order. It was 1 then 4, now it's 4 then 1. So what changed was the order of the terms, which means this is an example of the commutative property. Please be careful. Don't just assume because there are parentheses in there that it's associative. Associative is about grouping, and the grouping did not change here. So this is an example of the commutative property. All right, hopefully got that cleared up. A couple of important sets. We're going to use these when we talk about addition, subtraction, multiplication, division over the next couple of weeks. These are important sets for us. They're just sort of standard sets of numbers. Natural numbers will abbreviate with a bold-faced N. I can't really draw a bold-faced N, so what I'm going to do to represent natural numbers is that, to make it kind of look bold-faced. And natural numbers are the ones you can count on your fingers. It would be the set of 1, 2, 3, 4, and that keeps going forever. So that's the set of natural numbers. Up next, we have the set of whole numbers, which would be a bold-faced W. This is a really hard one for me to draw, so bear with me. Some of you who are more artistic will do much better with your bold-faced W. And whole numbers are just the natural numbers, but we throw in the one that looks like a whole, the 0. So 0, 1, 2, 3, 4, 5, and that keeps going. Oops, that keeps going forever. And then finally, integers. You might think we'd use a bold-faced I for integers, but any of you who have done like Algebra 2 or pre-calculus know that I has a different meaning altogether. We're going to stay away from I representing a set of numbers. Instead, integers is represented with a bold-faced Z. And the way I'll draw that will be kind of like the N, but it's just the Z version of it. There's our bold-faced Z to represent integers. I know it's weird to use Z for integers, but I has another purpose, so we can't use it here. And integers is going to be, the way that we'll describe integers is it's these whole numbers and their opposites. So what we do when we make the set of integers is we throw in negative numbers. And we'll have -2, -1, 0, 1, 2, and that goes on forever in both directions. So those three sets, we're going to bounce around a little bit from time to time. I just want to make sure you're familiar with those sets, what's included in them, and what the abbreviations mean. Are there any questions about those sets of numbers? All right. Closure. This is probably a new idea for you. The idea of commutative, associative, probably somewhere back in history, you've seen those before. Identity might be new, but not a hard one to make sense of. Closure is probably a new idea. And when we talk about closure, we're basically saying, is this a closed system? Closure for addition is if we add two numbers that are in a set, the result is also in that set. Meaning, this question here, is the set of whole numbers closed under addition? What that means is, if I were to add two whole numbers together, do I get a whole number back? I don't expect you to just know this sort of off the top of your head. I would expect you to throw some numbers in and see what happens. So is the set of whole numbers closed under addition? If you think you have an idea, it's just a yes or no question. There's no stakes here. What do you think? If I add two whole numbers, do I get a whole number as my answer? What do you think? And remember, this is one of those things where if we can find a counterexample, we can say it's false. Leslie says yes, Xochitl says yes, Michaela says yes. All right, a whole bunch of yeses. So let's look at an example. So if I take this whole number and I add it to this whole number, what I get is, sure enough, a whole number. So that worked. Now, one example doesn't necessarily prove it. Anytime I'm trying to decide if something's true or false, my approach is to look for a counterexample. If I can find one counterexample where this doesn't work, then I can say it's false. No, it's not closed under addition. But you know what? No matter what two whole numbers I try, what if I go as far to the edge of the whole numbers as I can get? 0 plus 4. No. You know what? No matter what, I'm going to try a few of these and then make my decision. And no matter what I try, I keep getting a whole number. So is the set of whole numbers closed under addition? Yes, it is. Because if I add two whole numbers together, I'm going to get another whole number. You try one. Just a true or false, I'll set up a poll for this. The set of integers is closed under addition. And just a true or false here. If you add two integers together, do you get an integer as your answer? Every single time. Has to be every single time for the answer to be true. If you can come up with a counterexample, then you can say false. It's important to know what the set of integers are here to answer this question. It's important to know what closed means. We're talking about addition. So if I add two integers, do I get an integer back? That's what this question is asking us. We'll go another 15 seconds on this, and then we'll talk about it. And my best advice on questions like this is to try some and see what happens. Don't just guess, try some, see what happens. You may convince yourself that it's true, or you may find a counterexample and then you know it's false. All right, let's see where we are on this one. Okay, kind of split between true and false. More truths, but we're split by a little bit. All right, so let's take a look at this then. I guess my question for those of you who said it was false, I would say, what's your counterexample? You could type it in over there for me. Because if you're going to say false, you should have a counterexample to support your reasoning. So if you have a counterexample, you can type it in there. That'll be just fine. If I take two integers and add them, let's say like 5 plus -3, that gives me 2. Those are integer, integer, integer. So that's closed. All right, well, what if you do two negatives? -4 plus -2, that's -6. Yeah, integer, integer, integer. You know what? No matter what two integers I add together, I'm going to get another integer. So the set of integers closed under addition, yeah, oh, I guess in this case, well, yes, it is. And for this question, we would say that that's a true statement. The set of integers is closed under addition. Hopefully that cleared that up. If not, let me know. We're going to talk about algorithms. What an algorithm is just, it's a fancy word. You hear it all the time with social media, an algorithm. The algorithm gave me that video to watch. Yeah, it sure did. An algorithm is a clearly defined method that works in all cases. The algorithm that gives you that video to watch takes all the information that you've provided it with and makes decisions to give you something else. But an algorithm doesn't have to be about computers. It doesn't have to be about math. It can be about brushing your teeth. There's an algorithm to that. You get your toothbrush. You take a cap off the toothpaste, you squeeze it onto the brush, you brush your teeth, you spit that out, you rinse. That's the algorithm. That's the method that works every time. Making a sandwich. You get two pieces of bread, you put something between them, whatever that might be, you close it up, and then you can eat your sandwich. You know, there are algorithms for lots of things, tying your shoelaces. So when we talk algorithm, it's not some mystical thing. It's strictly just a process that we use over and over and over again. Oh, go ahead, Courtney.
Okay, I'm going to turn my mic on. I hope that's okay.
It's totally fine.
So I guess I'm a little confused about what like if I see a set in the wild, like let's say the set is 1 and 2,
Yes.
how would I know what kind of set that is, whether it be natural, whole, or an integer?
That's an excellent question, Courtney. This set would be, and you know, we've talked set theory, so this is good. This set would be a subset of the natural numbers. It would also be a subset of the whole numbers. And it would also be a subset of the integers. So it could be in any of those. So this one set by itself, we don't really know if the universal set is natural, whole, or integers. The way that we're going to use those three sets really would be in questions like this, where we're going to talk about closure, we're going to talk about the sets of integers, and we're going to be very explicit that for this particular problem, we're talking about integers. For this particular problem, we're talking about naturals. For this particular problem, we're talking about whole numbers. If you were to just see a set out there in the wild by itself, then you don't really know what the universal set is. But that's okay. It's good to know that could be it is a subset of naturals, wholes, and integers. It's a subset of each of those.
So
Excellent
knowing,
question. I like that a lot. If that didn't answer it, you tell me. And if you have more questions, go ahead.
yeah, so it's not about knowing how to identify the set, it's more about what to do with what kind of set it is.
Yeah. Now, I could certainly give you a true false question and say something like this. I could give you a set that's -4, 3, 5 is a subset of the natural numbers. And I would hope you would recognize that that would be false because 4 is not a natural number. And then if a question said, you know, -4, 3, 5 is a subset of the integers, then that's true because the -4 is in the set of integers. So really, those three important sets, I just kind of want you to know what they are. They might come up from time to time, but hopefully I'm not going to ask anything that's odd, strange, or obscure that you didn't see coming.
Awesome. I appreciate it. So
Okay.
just to make sure we're on the same page, natural numbers is 1, 2, 3, 4, 5, and then like a whole number set would contain a zero, and then
Uh-huh.
the integers would contain a negative right
Yeah.
there.
Yeah. I mean, that's a very succinct way to say it.
Okay.
Naturals are what you can count on your fingers. Whole numbers include the zero, kind of looks like a hole. And then integers are just all the whole numbers plus their opposites, which would be the negative numbers. So, but the way you said it was great.
Thank you so much.
Yeah, sure. All right, let's talk algorithms. The standard algorithm for addition, what you've been doing since you were little. If we were going to add 369 plus 478, you tell me if you see something that looks strange, but we would do 369 plus 478, and we'd put a line underneath. One thing that's a little counterintuitive about this, we're all kind of trained to automatically do it and go over here and start in the ones column. But if I gave you money, if I gave you $100 bills, $10 bills, and $1 bills and said, see how much money we have, chances are you'd start by counting the hundreds first. You'd count the hundreds, then the tens, and then the ones. So it's a little bit counterintuitive for us to start in the ones. And we have to keep that in mind when we're teaching kids. Because if we were teaching kids, add that up any way you want, they'd probably start with the hundreds, not with the ones. So keep that in mind. Let's just talk about the process for this standard algorithm. What we would do here is we would say 9 plus 8 in the ones. That would be 17. We would put a 7 down here. And since I can't put and we looked at this a little with our other number bases. I'm going to go ahead and write it this way like we would with our other number bases. So I've got a 17 there, but I can't have 17 in the ones column. So I carry a 10 over there. I write down a 1, but what I've carried is a 10. Basically, I had 17 down here. That was too many. I took 10 of those and moved it over here as a 1 in the tens column. So yes, I wrote down a 1, but what I carried was a 10. I hope that makes sense. If it doesn't, you let me know. Then I do the same thing in the tens column. 1 plus 6 is 7, and 7, that's 14. I'm going to write the 4, and now I'm going to carry. I write down a 1, but what I've carried is actually 100 because it's 10 tens or 1 100 that I've actually carried. I write down a 1, but what I've carried is 100 or 10 tens. And now I can add those. 1 plus 3 is 4 plus 4 is 8. And I end up with 847 as my answer. Probably not a whole lot of strange in there, but you let me know if you see anything that doesn't look comfortable. We just added those. It's a little bit unusual that in our standard algorithm, we go start with the ones place, but that is our standard algorithm. What we're going to do next is we are going to look at some alternative algorithms. There are other ways to add numbers. You may think they're great. You may think they're terrible. Nobody's going to force you to use these, but I want you to know that they exist and what they're called. You may find that these, like if you're trying to help a child who's struggling with the standard algorithm, these kind of things might help to get them getting right answers. And then once they're getting right answers, maybe the standard algorithm starts to make more sense. Maybe these are a bridge to get you there, or maybe they're just kind of fun because they're different. So let's take a look at these alternative algorithms. The first one is called the partial sums algorithm. And instead of starting in the ones place, with the partial sums algorithm, we do what feels more natural. We start on the left and move to the right. In the partial sums algorithm, if we have 369 plus 478, instead of starting in the ones column, we're going to start in the hundreds column, which that's what you would do if I gave you a stack of bills. So let's see what happens here. One of the things with partial sums is we have to make sure we're aware of place value. This 3 right here, it's not just the number 3. What number does that 3 represent? $300. Excellent. Perfect. That represents 300. And so what I have here is I have 300 plus 400, and when I add those, I get 700. And I just write it down like 700. I've taken care of the hundreds column. Now I go over to the tens column, and I have this 6 plus this 7, but really it's not 6 plus 7. What does this 6 represent? It's not really 6. What is it? It's 60. Excellent. Very good. Very good. That's 60. And so really what I'm doing here is 60 plus 70. And so when I do 60 plus 70, 60 plus 70 gives me 130. And I'm going to write that down. And then finally, over on the right, I have 9 plus 8. And that 9 plus 8 is going to be 17. So I'll write that down as 17. The reason this is called partial sums is because I'm just doing a piece. I'm not getting the answer in one step. I'm doing a piece of it, a partial sum every time. I added the hundreds, I added the tens, I added the ones, and now I'll go back and finish this off by adding what I have left. 7 and 1 makes 8, 3 and 1 makes 4, 7. I still get 847. I better get the same answer I got before. But what we've done here is we've gone left to right, which is a little bit more intuitive, and we've looked at a different way to do it. It emphasizes place value, which I think there's a lot of value in that. There's a lot of good that comes from emphasizing place value. And that's the partial sums algorithm. We go left to right, and we just add up what we have each step of the way. Are there any questions on that before we look at another one? All right. The lattice method. The lattice method involves us drawing a lattice. If you've ever had like a lattice at your house, it's sort of an artistic thing. If we want to add 369 plus 478, what we're going to do with the lattice method is we are going to draw a box underneath this. Instead of just a line, we're going to draw a big rectangular box. And then we're going to section this off by place values. And then we're going to put in diagonals. So it's that's a really good question, Leslie. I think it could be that the standard is faster. But that's the beauty of these alternative algorithms. You know, some students are like, that partial sums is great. Why don't we always do this? Great question. Some people are like, yeah, I don't know about that partial sums. That's an awful lot to write down every time. Yeah, it's kind of true. And then some people are like, I love the lattice method. And other people will say, I don't like having to draw those boxes every time. So it's an excellent question, Leslie, and it's kind of a matter of personal preference. I really like that you guys will all know about these alternative algorithms, so you can use them if they come in handy. The lattice method, the way this works, what we've done by creating this box underneath, this lattice underneath, is we've created our place value positions. And here's what I mean by that. Lattice method will still start in the ones column like we would in the standard algorithm. When we go 9 plus 8 is 17. And what I'm going to do is I'm going to put the 1 here and the 7 here. Essentially what I've created is a tens place and a ones place. We move over to the left. We have 6 plus 7. That's 13. So I'll have a 1 here and a 3 here. And then we move over. 3 plus 4 is 7. We want to make sure we put the 7 down there, because in the number we're adding, essentially we have a ones place and a tens place, a ones place and a tens place, just for that number, just for those numbers we're adding. Then what happens with the lattice method, and here's kind of the beauty of it, is we extend those lines. Oh, I got to do it better than that. We extend those lines down, and now we add along the diagonals. So when I add along the diagonals, here I have just a 7. Here I have 1 plus 3, which is 4. And here I have 1 plus 7, which is 8. And I wind up with that same answer I better get every single time, 847. One of the things that's really cool about the lattice method is it takes care of the carrying for us. The carrying gets done every step of the way instead of having to do it in each step. It's built into the way that the problem gets drawn. And that's the lattice method. Some people love it. Why is the 7 an 8 now? Oh, that 7 became an 8 because we added these two numbers right here, this 1 plus this 7. So we add along the diagonal, that's 7. Here we add along the diagonal, 1 plus 3 became a 4. And here we add along the diagonal, 1 plus 7 became an 8. Perfect. Very good. Very good. All right, and that's just a couple of alternative algorithms for addition. I want you to be aware of them. I want you to know how they work. I want you to know how the standard algorithm works too, that when we carry, we're actually carrying a 10 or we're carrying 100. We're not just carrying 1. Let's talk a little bit about mental addition. If we wanted to add 68 plus 35 in our head, that's not that easy to do. But there are a couple of techniques we can use to do addition mentally. The first of those is called leading digit. And what you'll find is it's similar to partial sums. What we do is we look at the first digit of the number. So instead of looking at it as 68 and 35, we're going to break it apart. And we're going to say, okay, how about that 60 plus 30? Then I'll go back and pick up the 8 and the 5, plus 8 plus 5. And the reason there's value in this is we can do it in our head. 60 plus 30 is 90, plus 8 is 98, plus 5 more gives me 103. And by looking at the leading digits and just looking at those as 60 and 30, we can add this in our head. Another mental addition strategy is called compensation. What we do with compensation is we make one number bigger and the other one smaller by the same amount. So when I look at this one and I see 68 and 35, well, I don't like 68, but if I could make that 68 a little bit bigger, if I could make it bigger by 2 and then make the 35 smaller by 2, I have the same problem. This one got bigger by 2, this one got smaller by 2. So I haven't changed the value, but now I have something I can add in my head. 70 and 33, 103. And then break and bridge is kind of like leading digit a little bit. It's very much related to leading digit. I actually prefer leading digit, but break and bridge is a strategy that our book mentions. You may see it somewhere along the line in your elementary methods classes. If we have 68 plus 35, I can't do that in my head, but I could do 68 and 30 in my head, and then I'll finish it off by adding the 5. 68 and 30 would be 98, and then 5 more would make 103. Each of those are completely valid mental addition strategies. If you happen to like one, that's great. I want you to be aware of them, that there are things you can do to add these numbers in your head without trying to just figure out what 68 plus 35 is. You can change the numbers a little bit and be able to work with them mentally. I also want to talk a little bit about estimation. Whenever we're estimating, we don't need an exact answer. We're just coming up with an estimate. But we don't just want to throw some random number out there. We want to have a certain strategy to it. And there's a couple of strategies we're going to look at. One of those is leading digit estimation. If we want to add 45,327 plus 33,518, but we don't need an exact answer, we just want an estimate. One of the ways is leading digit. And so you just look at the leading digit. Okay, well, there's a 4 right here, so that's 40,000. And there's a 3 right here, so that's 30,000. So my estimate for this is 70,000. One of the things that's true about leading digit estimation is it's always going to be smaller than the actual answer, because essentially we're just getting rid of all of those things. So leading digit is okay, but it's always going to be smaller than the actual answer. And typically not that accurate, but maybe that's okay. We're just coming up with an estimate. Another approach is rounding, and we've done some rounding. If we look at those two numbers and we want to round, and let's say we want to round to the nearest 10,000. So I have 45,327, and I have 33,518. And if I want to round to the nearest 10,000, what I'll need to do is find the 10,000th place, which would be here. I'll look one space to the right. If that number is 5 or bigger, we'll round up. If it's 4 or lower, we'll round down. This one's 5 or bigger, so we'll round that up to 50,000. Do the same thing in the other number. We find the 10,000th place. We look one space to the right. Since that number is 4 or lower, we round this down to 30,000. 50,000 and 30,000 makes 80,000, and that's our estimate. And we did that using rounding. Rounding is going to be more accurate than leading digit in most cases, because we're 45,327 is closer to 50 than it was to 40. Last thing I want to talk about as far as addition's concerned are compatible numbers. Again, it's a way to come up with an estimate for an addition problem. And with compatible numbers, what we do is we look for things that point us in a certain direction. There's not really hard, fast rules for compatible numbers, but as I look at this, I see the 27 and the 75. Well, those two together is pretty much 100. And then when I look at the 161 and the 34, that's pretty much 200. And so I can add those together and come up with an estimate of 300 when I add all those numbers together. And so that's what compatible numbers are, is I look for things that, hey, I could put these two together and get something. And I could put these two together and get something. And now I can work with that in my head. So basically the mental addition and the compatible numbers are really good mental strategies. The estimation strategies for leading digit and rounding kind of depends on how close we want to be to our answer, to our actual answer, because an estimate doesn't have to be exactly right. All right, let's take like 2 minutes and we'll start back up at 11:45 and we'll talk about section 3.2, which is subtraction. If you have any questions about addition, you can throw those my way while we're waiting to dive into subtraction. Seems like we're doing really good with the addition topics. I hope that's true. Here, let's dive into subtraction. It's going to look pretty familiar. We're going to talk properties. We're going to talk commutative, associative, and identity. And as far as the commutative property goes, remember the commutative property is about order. And so if I say 7 minus 5, is that equal to 5 minus 7? Is 7 minus 5 the same as 5 minus 7? I promise it's not a trick question, Leslie. No, it's not. 7 minus 5 would be 2. 5 minus 7 would be negative 2. So those two are not equal to each other. And so there is not a commutative property for subtraction. We had a commutative property for addition, but we don't have one for subtraction because it doesn't work. Okay, let's see if there's an associative property for subtraction. And I'm just making up numbers. There's nothing magic about these. But if we say 5 minus 4 minus 3, would that be the same as 5 minus 4 minus 3? Take a second and check. Remember, order of operations, parentheses go first. I've changed the grouping, so it's an idea of, does the associative property work here? You let me know whether or not that works. I've got no's again. Let's see here. On the left-hand side, that would be 1 minus 3 or negative 2. Oh, I guess I should have that. And on the right-hand side, I have 5 minus 1, which is 4. Sure enough, that did not work. Associative property does not work for subtraction. We do not have an associative property for subtraction. When we go talk about identity, identity property had to do with 0. 5 minus 0 equals 5. Well, that looks okay. Do we have an identity property for subtraction? And I realize we just talked about it, so it's fresh in your head, hopefully, but it's also brand new. So, and if we don't have an identity property for subtraction, why not? Perfect, Natalie. Because in order to have an identity property, it has to work both ways. And if I do it the other way, 0 minus 5 is negative 5. When I subtract 5, now this 5 has lost its identity. It's not 5 anymore. Now it's negative 5. And because of this, it needs to work both ways, and it does not. So we do not have an identity property for subtraction. So all three of these properties work for addition. None of them work for subtraction. There's no commutative, there's no associative, there's no identity. We had them for addition, but they don't work for subtraction. We talked about our 3 important sets, and we talked about closure. So now I'm going to ask you a true or false question. The set of whole numbers is closed under subtraction. And this is just a true or false question. The set of whole numbers is closed under subtraction. So remember, closed means if I use 2 of those and I do this operation, I get one of those back. So what this question is asking you is, if you subtract one whole number from another, is your answer a whole number every single time? That's what this is saying. In order for this to be true, whole number minus whole number has to give you whole number every single time. One thing I can say while you work on this one is the set of whole numbers is closed under addition. If I add a whole number to a whole number, I get another whole number. Now we're doing subtraction though. Maybe the same, it might not. We'll go another 10 seconds on this and then talk about it. Okay, let's see. Really strong agreement. Not quite unanimous, but really close. That's great. That's great. That's good. The idea of closure is probably new for almost everybody. And so this means you have a pretty good sense of it, which is awesome. So the set of whole numbers is closed under subtraction. Well, if I do 7 minus 5, I get a whole number. Whole number minus whole number equals whole number. Yeah, but that's just one example. That doesn't mean it's true all the time. In order to show this false, I just need one counterexample. And if I try like 3 minus 6 and get negative 3, now I have whole number, that is not a whole number. So this counterexample right here convinces me that this is false, because there's one where I did whole number minus whole number. My answer was not a whole number. It's an integer, but it's not a whole number. And so this would be false. We talked about algorithms for addition. We're also going to talk about algorithms for subtraction. Our standard algorithm for subtraction, that's where we're going to start. If we want to do 732 minus 155. Here again, maybe slightly counterintuitive, we're going to start in the ones column. If you see something here you're not sure of, it doesn't make sense, you don't know where that number came from, that's not the way I do it. Those are all perfectly reasonable things to bring up. Here I would go to the ones column, and what I would like to do is 2 minus 5, but I can't do 2 minus 5, so instead I have to borrow. And by borrow, what we mean is I'm going to reduce this by 1. But really what I've done is I've taken 10 from there. This is in the tens column. So by reducing that from a 3 to a 2, I'm borrowing 10. And I take those 10 and I rewrite them as ones over here. I'm hoping you see now why we did the stuff with the other number bases, because now this is falling right in line with it. Anyway, so what I've done is and some in your methods class, your methods of teaching elementary school math, your professor might call this trading instead of borrowing. And I think that's a great terminology, because what we've done is we've traded one of those 10s so that we could have 10 ones. We've traded. Okay, borrow, trade, whatever terminology you want, that's what we're doing. And then we can subtract the 12 minus 5 and get 7 down at the bottom. Now I go over to the tens column, and what I would like to do here is 2 minus 5, but I can't. Instead, I'm going to have to borrow again. And now I'm borrowing 100 from here, and that's going to give me 10 tens over there. And now I can subtract, and I'll do that. 12 minus 5 will give me a 7 at the bottom. 6 minus 1 I can actually do, and I end up with an answer of 577. If you see anything there that doesn't make sense or you don't like, let me know. Key thing I want you to take away from this is when we borrow from here, we're borrowing 10. And when we borrow from here, we're borrowing 100. Not just 1, we're borrowing 10, we're borrowing 100. Same thing as when we carried 10 or carried 100. Hopefully that makes sense. Let's look at some alternative algorithms for subtraction. Just like the ones we looked at for addition, you might think these are great. You might think these are not so great. But we're going to go ahead and do some exploration with these. The sense I got was that you kind of, if we were in a room together, I'd be able to get a real sense of it, that you kind of like the partial sums and the lattice. We'll see if you like the Indian-European algorithm. The Indian-European algorithm, we're going to set up our problem the same way with 732 minus 155. But instead of starting in the ones column, we're actually going to start on the left. The Indian European algorithm. So it's sort of disputed where this originated, whether it was in India or in Europe. I think historically I've called it the Indian algorithm, but then I had students from Europe tell me, hey, this is how I was taught when I was a kid. So maybe it's the European algorithm. I'm not exactly sure. So we'll just kind of go with both on those. If you see either of these names, the Indian algorithm or the European algorithm on a quiz or an exam, this is the algorithm it's talking about. So with this algorithm, we're going to go left to right. And the little note that I've got there is we're going to borrow from the answer. And I'll talk about that here in just a second. We're going to go left to right. So I start out doing this problem, and I'll do 7 minus 1, that's 6. So far, so good. Now I go over to the tens place, and I think, well, 3 minus 5. I would love to do 3 minus 5, but I can't. What I need to do is borrow. What's different about this algorithm is I'm going to borrow from the answer. So instead of taking 100 from here, I'm going to borrow it from down here. Then that 6 is going to become a 5. I borrowed 100, so this gets to go up and become 13. And now I can subtract in my tens column. Might feel a little strange, but left to right is how we read. Left to right is how you would count a stack of bills if I gave them to you. We did 7 minus 1 got 6, and then I needed to borrow. Okay, instead of borrowing from here, I'm going to borrow from down here. Then I'll do 13 minus 5. Okay, well, 13 minus 5, that's fine. That's just 8. Okay, now we'll go over to the ones place, and in the ones place, I need to do 2 minus 5, but I can't. Can't do 2 minus 5, I'm going to have to borrow. When I borrow, I'm going to borrow from my answer. That becomes a 7. This becomes a 12. 12 minus 5 is 7, and there's my answer of 577. Same answer I got the other way. It better be. The kicker here is we go left to right, and our borrowing is done from the answer. I'll tell you one of the reasons, there's 2 reasons I kind of like this one. I don't know that I would advocate for it across every elementary school in America, but one of the reasons, there are 2 reasons I like this. One is we go left to right, same way we read, same way we would count numbers if we were given them. Another reason I like it is in our standard algorithm, sometimes you have to change a number twice. And students get confused when that happens. Here's what I mean by that. So in our standard algorithm, when we have 732, the first thing I need to do is I need to cross this number out, make it a 2, and then this becomes 12. And then I can subtract. And then I cross this number out, it becomes a 6, and I got to change this number again. And that can be a source of confusion for students because sometimes they want to make it 13. Sometimes they just want to make it 10. Like the changing this number a second time is sometimes hard for students. And the Indian European algorithm avoids that. You never change a number twice. So that is one of the advantages I see to it. You might think, yeah, I don't really love borrowing from the answer. That's okay. That's just fine. We may have a chance to practice one of those in a little bit. For right now, I want to jump ahead and look at something different. Oh, no, I am going to have you practice one. Wait. Yes, I do want you to practice one. I'm sorry, I apologize. I'm getting myself in a hurry. I want you to practice that Indian European algorithm. Try 312 minus 175. I'm not going to set up a poll for this because it's not as much about the answer as it is about how you did it. I want you to try 312 minus 175 using the Indian algorithm. And then we'll talk about it just to kind of solidify what we're doing there. So try this one using the Indian/European algorithm, and then we'll talk about how that's done just to make sure that you have a sense of it. All right, I'm going to do it. You let me know if you see something that you're not sure where it came from or why it happened. We're going to go left to right, and when we borrow, we're going to borrow from our answer. So 3 minus 1 is 2. That's fine. 1 minus 7 I can't do. 1 minus 7 I can't do, so I'm going to have to borrow from here, and that 1 is going to become 11 because I borrowed 100, which is 10 tens. 11 minus 7 is 4. Now I'd like to subtract 2 minus 5, but I can't, so I need to borrow from here. That's going to become 12. 12 minus 5 is 7, and then I have an answer of 137. And this is easy enough to check. We can make sure we have the right answer here. We can just do, if I do, 312 minus 175, I better get 137. Sure enough. Hopefully that made sense, and we're borrowing from the answer instead of borrowing in the problem. Let's look at another alternative algorithm. This one's called the New Zealand algorithm. This one, and you can kind of see from the words there's some notes. We go right to left. So we start in the ones place. We increase the top and the bottom number. We don't do any borrowing. And here's what that looks like. If I have 732 minus 155, and I want to subtract those, we're going to go right to left. So it's the same as what we're used to with our standard algorithm. And I'm going to try to do 2 minus 5, and I can't do it. What I'm going to do here is I'm not going to borrow, I'm not going to trade, I'm not going to do any of that. What I'm going to do is I'm going to make the top number bigger by 10 so that I can do the subtraction. But if I make the bottom number bigger by 10 to keep the integrity of my problem, I also have to increase the bottom number by 10. Well, I don't want to increase this one by 10 because that puts me right back where I was with not able to do it. But what I'll do is I'll increase the bottom number by 10 right there. So I've added 10 to the top number in the ones column. I've added 10 to the bottom number in the tens column. And this is the New Zealand algorithm. I believe it's how it's taught in New Zealand. I can't confirm that, but that is what it's called. Now I can do 12 minus 5 over there in the ones column and get 7. I move over to the tens column, and boy, I sure would like to do 3 minus 6, but I can't. So what I'm going to have to do is I'm going to have to increase this to 13. I've increased it by 10 tens, or 100. Well, if I increase the top number by 100, I need to increase the bottom number by 100. You'll notice I haven't borrowed anything. All I did was make the top number bigger and make the bottom number bigger by the same amount. Now we can subtract that. 13 minus 6 gives me 7, and 7 minus 2 is 5, and I have 577. That's the problem we started with our standard algorithm. That's the same answer that we got when we used the standard algorithm for it. I'm going to have you practice one of these too. This might be the most strange of all the ones we've done because the adding ones seem pretty comfortable right away. Partial sums, lattice method, okay. And then we get to the Indian European way. Okay, I'm just borrowing, but I'm borrowing from the answer. It's different. Yeah, Nicole does not like this one. That's fair. That is fair. Let's try another one, the New Zealand algorithm, because we don't do any borrowing. And we're kind of used to borrowing. So 372 minus 175, try this one. I'll give you a little time to try it with the New Zealand method, and then we'll do it together. And I kind of see these as, well, I think they're kind of cool to know about, and they could be used for remediation with kids who might be having trouble. Just, how about I show you this way? And maybe it clicks for them. Because in other parts of the world, very specific parts of the world, I'll admit, because most of the world uses the standard algorithm, but there are places where other things are done, and they're completely valid. So the things to remember with the New Zealand algorithm are that we go right to left, but we don't do any borrowing at all. Instead, we increase the top and bottom by the same amount. So here I'd like to do 2 minus 5, but I can't. So I need to make that bigger by 10. Well, if I make that number bigger by 10, then I also need to make this number bigger by 10. And then 12 minus 5 is 7. 7 minus 6 is 1. 3 minus 1 is 2. And we have 217. 372 minus 155. Oh, I wrote the problem down wrong. Haha. I was like, this isn't working out though I thought it would. All right, how about I fix that? How about we do it the right way? 372 minus 175. There we go. Sorry about that. Let's clean this up a bit. If you got a different answer than me, that's because you probably did the actual problem that was on the page and not the one that I wrote down incorrectly. So we get another shot at it. 2 minus 5, I can't do. That's going to get bigger by 10. And I make this bigger by 10 also. 12 minus 5 is 7. So far, so good. 7 minus 8, I can't do. So I need to make this bigger by 10, or actually it's bigger by 100, and make this smaller by 100. Oh, wait, make this bigger by 100. What's going on in my brain? 17 minus 8 is 9. 3 minus 2 is 1, and we get 197. So with the New Zealand method, and I think this is the hardest one to wrap our head around because we're so used to borrowing something. But in this one, all we do is make that one bigger, make this one bigger to go along with it. Make that one bigger, make this one bigger to go along with it. So I think this is the most strange of the alternative algorithms we've looked at. Let's look at some subtraction problems. This is called the counting up strategy, and I'm going to let you try it before we talk about that name. Marissa woke up at 5:52 a.m., went for a run, had breakfast, read the news, took a shower, and left for work at 7:35 a.m. How long was she awake before she left for work? I'm going to set up a poll for this one, and then we'll talk about it. And what those answers are in terms of hours and then minutes. So like the top answer is 1 hour and 17 minutes. So that's how those answers are written. And there's not necessarily a right or a wrong way to go about this. Kind of leans back into our problem solving back at the beginning of the course a little bit. We'll go another 20 seconds and then talk about this one. Okay, strong agreement, not unanimous. So let's take a look. So there's a couple different ways you could go here. There's a lot of different ways you could go here. Um, the reason this is called the counting up strategy is even though this is kind of a subtraction problem, not very many of us are going to go 7:35 a.m. minus 5:52 a.m. That's just not really, there is a subtraction element here, but it's pretty unusual to approach it that way. Instead, a lot of subtraction problems lead us towards what's called the counting up strategy. And you may not have done this exactly, but maybe some variation of it. If we start at 5:52 a.m., and essentially what we're going to do is we're going to count forward until we get to 7:35 a.m. somehow. Now, my first thought is, okay, well, if I do an hour, that gets me to 6:52 a.m. I'm not quite there yet. I still need to keep going. And then this is how my brain does it. Yours might be a little different. But then I'm going to do 8 minutes to get me to 7 o'clock. And then 35 more minutes will finish it off. And then I'll put those two together and have 43 minutes. And so the total time was an hour and 43 minutes. That's just one approach. You could do this differently. You might say, well, if I go forward 2 hours and then back up 17 minutes, that would get me to an hour and 43. That's a perfectly reasonable way to go also. But I think what is most common for people to do is something that involves counting forward. We start here and we count forward until we get to this answer. And it may involve going forward 2 hours and being 7:52 and then saying, okay, take away 17 minutes. Perfect. That's fine. But the idea is we don't just set up a straight subtraction problem for something like this. If you have any questions or comments or anything you want to share about that one, you absolutely can. Just let me know. Oh, it would look exactly like this. And then you would type 143 for your answer. So it could look exactly like this. And there'd be instructions on how to type your answer. And that's what your answer would look like. Oh, all right. All right. This is, I don't know if this is exactly counting up strategy, but counting up is in there. So we'll leave it under that same heading. Joshua was driving from Billings, Montana to Lewistown, Montana. When he left Billings, his odometer, that's the thing in your car that tells you how many miles are on your car, read 42,177. He made it to Lewistown and headed back to Billings. So just to sort of sketch this, he's in Billings. He drove to Lewistown. Now he's on his way back. When he was 38 miles from Billings on the way home, his odometer read 42,389. So the question is, how far is it from Billings to Lewistown? The key here is the odometer. Keep in mind that he still has 38 miles to go to finish off his round trip. I'm going to set up a poll for this one. If you struggle with this one a little, that's okay. If you get it right, that's fantastic. There's a couple of things to keep in mind here. His starting odometer reading, and then what is his odometer going to read when he's all done with his trip, right? He still has 38 miles to go. So what's his odometer going to say when he's all done? And that will tell us how far it was for the round trip, Billings to Lewistown and back. This is one of those questions that when you first read it, it feels pretty complicated. And then when we talk through it and you see it done, I'm hopeful, and you can let me know if I'm wrong. It's one where the light bulb goes on and it's like, oh, okay, that's what you do here. And this is our last poll for today. I can tell you that we're close to finishing up. I do want you to try it. If you get an answer that's not one of the ones shown, that's okay. Pick the one that's closest to it. And I guess the counting up in here is really just factoring in that 38 miles that he still has to go. One of the things I definitely want you to reason this out. Sometimes if we read a problem and we're not sure what to do at the beginning, there can be a tendency to panic and just do something with the numbers. Instead, reason it out, think about what we're really trying to do here, and then come up with an answer. Drawing a little picture, even a rudimentary one like the one I have, can help. Let's go another 10 seconds and we'll take a look. Four, two, three, two. That's unusual. Okay, so we'll take our time through this one. Let's talk through this a little here. All right. So he started in Billings, and when he was in Billings, his odometer said 42,177. He drove to Lewistown. He turned around and he was driving back, and when he was here, not quite home yet, it said 42,389. So he still has 38 miles to go. He still has 38 more miles to go. So we need to add that 38 to this number to figure out what his odometer is going to say when he gets home. So we'll add that to it. So 42,389 plus 38. So when he gets home, his odometer is going to say 42,427. You let me know if something doesn't make sense. All right, so at the start of this trip, his odometer said that. At the end of his trip, it said that. So now we can subtract to figure out how far he drove. 42,427 minus the 42,177. That'll give us how far he drove round trip. 250 miles. Well, that's the round trip distance, and this question just said, how far is it from Billings to Lewistown? So that's just one way. So instead of the round trip, we just need one way, so we'll cut that in half. 250 divided by 2 is 125. Hopefully after seeing it, it's like, oh, okay, that makes perfect sense. You'll get a chance to practice one like this in the homework. One last thing I want to say about the homework is number 31 is a fun question about a mule and a horse. It's for fun. I hope you get it. We can talk about it next time, but it's not a